Hello. This will be the first in a lecture series on college algebra. Today we're going to look at the first chapter in the OpenStax College Algebra book. I'm going to be using the OpenStax book as a kind of guide, but I won't be following it necessarily religiously. I just like to have a text as a resource. So if you wanted to do some exercises from these sections, you can do so. I will put the links to the OpenStax and the OpenStax College Algebra book in the description, which you can find and read through. Today we'll call this lecture 1, and we're going to talk about the real numbers, which we will construct from sets of other numbering systems, not quite systems, but numbers of sets. The first one we will call the natural numbers. The natural numbers are the numbers 1, 2, 3, 4, 5, etc. These three dots we will mean continues. And if there's nothing on the other side of this dot, 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 that means it goes on forever. Now, set notation, we use these squiggly lines to denote a set. In other words, we will have a set, say, that has this elements A, B, and C. The squiggly lines will let us know that what we have is a set. My squiggly lines are not great, so bear with me. I think in context, you'll understand. So because the natural numbers are used often, we have a special notation for them. We call it this fancy n. The fancy n equals the set, again, 1, 2, 3, etc. forever. Now, the book uses the notion of a whole number set, and the whole numbers are just the natural numbers, and we're going to have a fancy W. I don't like that. Let's do it like this. And it's basically just the natural numbers with 0. The book does it. I might have made the caveat, the natural numbers, and added 0 to it. Some professors do that. Others leave it as is. But this is how we'll do it. So we have the natural numbers and the whole numbers. Another important set is something we call the integers. integers. And the integers are the natural numbers and 0, or the whole numbers, and the negative of each. So in other words, we will write it like this, because we want to denote that it's infinite in either direction. So we'll start at some point, and we'll go on forever. You can write out many more terms if you want to. In other words, my starting at -2, -1, 0 is just a choice. You don't have to do it that way. You could start -100 and count down from 100 to 0, but I like to keep it short. So that is the set of integers, and notice we have positive integers, which of course are 1, 2, 3. Negative integers, which will be -3, -2, -1, and of course 0, which is just a set that has 0 in it. So positive integers are basically the natural numbers as we defined it, with 0, which is the whole numbers, and then the negative of the positive integers. And we have a special notation for the integers as well, because we use the notion of the integer a ton. So it's a fancy z, and the fancy z again will be the set that has all of the counting numbers 0 and their negative. Now, why z? Why not I? We have w is whole, n is natural, z is integers. It's a German word, Zahlen, which means numbers. So somewhere along the mathematical continuum, somebody decided that the integers were going to be called Zahlen, Z, and that's the notation we use. All right, so now we have the natural numbers, whole numbers, the integers, and an important concept, again, another numbering set. So we'll call these the rational numbers. And the rational numbers, we have to be a little more fine with it. And so we define the rational numbers as the set of a fraction a over b such that a is an integer, b is an integer, and b is not equal to 0. So a couple notes just to be consistent here. We have the set notation, and then we have this little vertical line. This means such that. So when we read the set, it says the set that contains a over b such that, and then we have a definition of a as an integer, b as an integer, and b is non-zero. A better way to write this, of course, would be to shorten the ab as an integer. And to do that, we need another notation, which looks a little like an e, and which means element of, or sometimes just in. So if I want to say that a is in a set, I do this. And since we have the integers, remember fancy z is the integers. So this means a is in the integers. And it's just a more concise way to write this definition. So a over b, where a and b are integers and b is non-zero. Meaning b could be anything but 0. Okay, so that's how we have the rationals defined. And this also has a special notation, the fancy Q, which again is a and b in the integers, where b is non-zero. Now notice we're not listing them like we did with the naturals, wholes, or integers. It's sufficient to write it this way, but we could write out a bunch of rational numbers, but this is a little bit difficult. We can do, say, 1 over 2, 1 over 3, 1 over 4, but we have to include 2 over 2, 3 over 2, 4 over 2. So the ordering can be a little tricky, so we just write the definition this way. Now the Q comes from just the word quotient, which is a fraction. Okay, so a little bit of explanation of what this means. So if I have 15/4, 15/4 is a fraction. In fact, 15/4 is 3.75. We say 15/4 is a rational number. It's in Q. Notice that I can write it as a decimal. Now, what's important about this decimal is we say this decimal terminates. It stops. It's 3.75, that's it. And let's look at something a little more tricky. 4/11 is 0.363636, and so on. It doesn't stop. It's always 3636. We write this when it repeats. We put a line over the parts that repeat. So 3 and 6 repeat, so 363636. Notice this does not terminate. So it does not terminate. But repeats. This is important because when we define what's an irrational number, we're going to use a little bit of this terminology. So we have what's called rational numbers. Now we have what's something called irrational numbers. Now, irrational numbers have a particularly unsatisfying definition as being not rational. And remember, the definition of rational means we can express as a fraction where a and b are integers and b is non-zero. So we can think of irrational numbers as not expressible as a fraction of integers. That part's important, the integers part. Meaning if I have, say, the square root of 2, some of you might have already noticed that I can write the square root of 2 as a fraction, the square root of 2 over 1. But the square root of 2 is not an integer. So I cannot express the square root of 2 this way and say it's rational. The square root of 2, I would need it to equal a and b, where a and b are integers and b is non-zero. If I can do that, then the square root of 2 is rational, but we cannot express it that way. Now, another fact, the square root of 2, let's say, as an example, is square root of 2 is 1.4, approximately, 142 ... This does not terminate and does not repeat. So we can also think of irrational numbers as non-repeating, non-terminating decimals. And this is convenient as well, though it's impossible to say that something doesn't repeat that's infinite, because we can never know exactly every single digit. There are people that have looked at pi, for example, to many digits, and they have yet to find a repeating pattern in pi. So pi is a non-repeating, non-terminating decimal. And so pi is irrational, like the square root of 2. So those are common examples of irrational numbers. You can think of many more. There are infinitely many of them, just like there are infinitely many rational numbers. This gets a little bit into set operations that we don't want to get into here, but sometimes we express the set of irrationals as the real numbers without the rational numbers. Now, why would this be true? Well, if I'm given any number the number is either rational or irrational. And the caveat is never both. It can never be both rational and irrational. So given every number, it's either rational or irrational. So the real numbers without the rationals, meaning I take the reals and throw out all the rational numbers, I'm left with the irrationals. So sometimes we express it that way. So now what we have is the real numbers when we combine all of these lovely sets of numbers. So when we combine the rationals and irrationals, we get the set of reals. Reals are constructible on a number line. So let's say we have a number line. I'm going to plot out just some markers here. I'll do the integers. So the real numbers are every point on this line, including the integers, including the whole numbers, including the natural numbers. So for instance, I could plot the square root of 2, which we said is about 1.4. So that guy would be here. We know that pi is 3.14, etc. That would be approximately here. Conversely, we would have negative pi would be somewhere over here. And then the negative square root of 2 would be somewhere here. So every point on this number line, it corresponds to a real number. And these go on into the infinite and negative infinite direction. So we can pull any point, and that'll represent some real number. All right, so why do we need all of these designations? Well, partly because it's convenient when we're talking about particular numbers, solutions to equations. If we talk about set operations, we have numbers of integers combined with numbers of irrational numbers, so on. But notice something, we can express these number systems. I don't know if systems is a great word. It's called number sets as a picture. Some of you are probably familiar with the Venn diagrams, where if I have a set here, a set here, the intersection of these two sets is the colored in spot. So it means that they intersect. So these numbers will correspond in this way. So let's say this guy is the natural numbers. Now the whole numbers are the natural numbers with 0. So I'll just not write that for now. Let's just have the natural numbers. I don't love that either. There. In the integers, our lovely z is this set, and you can see inside the integers we are contained with the natural numbers, and then inside that we have the rational numbers, and of course encompassing all of these are the real. So if I use the concept of containment, we won't get too deep into this. This means subset. It's a way to denote what we've just drawn. So the natural numbers are a subset of the integers, are a subset of the rational numbers, are a subset of the real numbers. So what does that mean? Well, the first thing is we want to think about how can we classify numbers. And a number can be in more than one set. So for instance, example, 1/2. What kind of number is 1/2? Well, we know it's a real number because all numbers are real numbers. Any number you can think of is a real number. So 1/2 is rational because I can express it as a fraction of integers. 1 is an integer, 2 is an integer. It's not an integer because it's a fraction, and it's a real number. So you can see I can define 1/2 as a rational number and a real number. How about 2? How can we define 2? Well, we know that 2 is a natural number just by our set above. And we know that any natural number is also an integer. So 2 is a natural number and it's an integer. Now it's a rational number. Now, how is it a rational number? Well, because I can express 2 as 2 over 1. 2 is an integer, 1 is an integer, 1 is not 0, so it's also rational. So everything's real, so it's a real. So 2 is natural, integer, rational, and real. In other words, if we look, 2 exists in this, which means it exists in here, and exists in here, and exists in here. How about the square root of 3? Well, 3 is prime, so I know I can't break up 3 other than 3 times 1. I also know that if I were to write this decimal expansion, it would be non-repeating, non-terminating. You can put it in your calculator, and your calculator will terminate it just because it's impossible to list an infinite list of numbers. So this is irrational and real. Now, why isn't my irrationals part of this? Well, it just, the irrationals are a subset of the real numbers, but the naturals, integers, and rationals aren't subsets of the irrationals. So the only relationship between the irrationals and the reals is this. It doesn't fit nicely in that set containment. So we just sort of think of that differently. All right, so let's look at some examples, and this will be classification. We just want to see if I give numbers, where are they, or what are they? So an example would be, let's identify these. Identify as, let's say, rational, irrational, whole, and natural. So that's it. We want to identify them as one of these. So we have A, B, C, and D. Let's do square root of 2, 37, 11/12, and 0. All right, so we just have to identify these based upon our definitions above. Square root of 2, I think we've talked about. This is irrational. I know it's real, but we only want to classify them in as real, or sorry, rational, irrational, whole, or natural. Now 37 is a whole number, and it's a natural number. The more you do these and think about it, the whole natural is going to dissolve into just basically the naturals with 0. But for now, let's keep them separate. 11 halves, you can, this is a fraction. 11's an integer, 12's an integer, so we say this is rational. Now 0, we can express 0 as a fraction, but that's not really one of our choices. So we'll say 0 is a whole number because we're not including 0 in our naturals. But one aside, I said 0 was a rational number because anything divided by 0 is, or any number that divides into 0 is 0. So I can really take any integer and express 0 as a fraction. So technically 0 is a rational number. It can be expressed as a fraction of integers. All right, so let's do a little bit of our set notation. So let's say classify as natural, integer, rational. I'm going to use this as a symbol of irrational. Your book does, or the book does this. I don't love that either, but we'll just use the reals without the rationals. So we have A, B, C, D. Let's look at the square root of 49. Say 8/3. Then I have 1, 2, 1, 2, 2, 1, 2, 2, 2, 1, 2, 2, 2, 2. Repeating that pattern. and the square root of 19. All right, so we want to classify these as natural, integers, rational, irrational, and real. So let's take these one by one. The square root of 49 can be evaluated. That's 7. Well, that's an integer, a natural number, a rational number, and a real number. Technically, it's a whole number too, but that wasn't one of our choices. So B is 8/3. 8/3 is 2.666 forever, which we can write, again, we put the little line on top of it to denote that this part repeats forever. But we can see we can express it as a integer divided by an integer or a fraction. And so this is rational and, of course, real. Now, what about 3.121221222122221, so on? Is this rational? Is this irrational? Is it real? Well, of course it's real. It's not natural. It's not an integer. The question really is this a rational number or irrational number? Well, this goes on forever by the ... And if you can sense that what's happening is I'm adding one more 2 between the ones. This doesn't repeat. As much as it looks like there's a pattern, it does not repeat. Because it doesn't repeat or doesn't terminate means that it is irrational. This will never be expressible as a fraction. It's a non-repeating, non-terminating decimal. And finally, square root of 19. Again, 19 is prime. So this cannot be expressed as a fraction. It will be a non-repeating, non-terminating decimal. So this is also an irrational number. All right. So that ends the look at the real numbers. Hopefully this made sense. Again, you could try some of the exercises in the book. A lot of it's just classification of numbers, similar to the examples we did here. So that's it for lecture 1. Stay tuned for lectures 2 and so on. I think the next set will be order of operations. The next set of lectures will be order of operations and still in the prerequisite preliminary stages. So look out for that. Please like and subscribe, and I appreciate you watching.